Welcome to the class Data Science for Psychology and Neuroscience. This is an undergraduate level and graduate level course on the principles of data science as they are typically used in scientific research in psychology and neuroscience. This first lecture here, we will go over the idea of data science, which is essentially the art of data investigations. Data science itself sits at the interface between three very large disciplines. On one side, you have engineering, whose focus is on building systems. On the other side, you have art and design, whose goal is to communicate. And then you also have the scientific part, whose principal goal is understanding. Now, within these general areas, data science arose specifically at the interaction between three very specific fields: computer engineering, graphic design, and statistics. Computer engineering is focused on issues of data formats, data architectures, computing speed, the process of computing itself. Graphic design is focused on visual organization, aesthetics, intuitive design, and statistics, which is probably the most closely linked to data science. It's focused on model building, hypothesis testing, developing metrics and measures. And data science really sits right in between these three fields. Now, there are other overlapping fields as well. So, for example, the field of data visualization sits at the interface between statistics and graphic design. Rendering sits at the interface between computer engineering and graphic design. Machine learning sits at the interface between computer engineering and statistics, but data science is the only field that sits right in between all three. And throughout the course of this class, you will see examples about how, for example, data visualization is relevant for understanding the structure of your models, or how limitations in computing can determine what you can or cannot solve in statistics. Okay, so far we've presented data science by aligning it to these three general fields, but let's give it a formal definition. Wikipedia has a pretty good definition, at least as of the time of this recording. It defines data science as an interdisciplinary field that uses scientific methods, processes, algorithms, and systems to extract knowledge and insights from many structural and unstructured data. Essentially, what data science is trying to do is answer the question, what is the story that the data is trying to tell you? So let's think about the process of data investigations with data science. Like any other investigative process, whether it be journalism or criminal detective work, there are general principles of trying to understand the clues that you're given and how they relate to the underlying story of what happened that you can use as a guidepost when you're building your data analytic tools in order to solve some data problem in your research. So let's jump to the principles of data investigations that we really just borrowed from principles of criminal and crime scene investigations. First, you want to clearly identify what you were asking. You want to understand the structure of the question that needs to be answered. In, let's say, a crime scene from Sherlock Holmes, that's pretty easy. It's a body on the floor. If you're doing research in the relationship between physical contact and sense of, companionship between two individuals, well, there your question is, how does some metric of physical contact relate to some metric of closeness between two individuals? You really need to narrow down the question, and this is often an overlooked part of data science. Next, you want to determine the parameters and constraints of your query. What is the range of places that you can gather evidence and clues? What are some limitations or things that you cannot do? Then you want to know the context of your evidence, and this is really important. Your evidence, in this case the data that you have on hand, arose from some thing, whether it be an experiment, a natural survey, some instrument data. And the context in which it was collected is just as valuable to understanding the nature of the relationships in your data as any statistical metric. So you always want to consider the context of where your data comes from when trying to understand the story it's trying to tell. You want to be systematic in your search. You want to have a set of procedures for thinking about your data. We will go over a series of steps in thinking about your data, from initial visualization to characterizing the nature of the distributions of your data, understanding the assumptions of statistical methods and what different methods can do, how to interpret, how to evaluate hypotheses and gather evidence towards or against hypotheses. Each one of these abilities you will learn over the course of this class is designed to be parts in a system that go from raw physical evidence to a data scientific story. You also want to disturb the data as little as possible. You want to have your data be as close to the origin point as possible. So things like data transformations, removal of outliers, etc., are all often heuristics for trying to make your statistics work. But in many cases, it's not a problem of making your data fit the assumptions of your statistic. It's more a matter of finding the right statistic to analyze your data, given its messiness. So we're going to focus on thinking about the variety of tools at your disposal for looking at your data that minimize the need to transform or change your data in order to fit any individual statistical constraint. Next, you want to see the story from as many perspectives as possible. There are many possible ways that the data you see could have arisen, and many possible hypotheses that could have generated the data that you see. And you want to think about all of those possibilities, and you want to directly evaluate them. So we're going to go over issues of model selection and feature selection, how to think about the nature of the model you're trying to build in order to explain the data that you observe. You also want to strive for simplicity over control. The rule of parsimony is strong in science, and in data science, it's a core principle. The simplest model is often the most truth-conducive. So we're going to focus on why that is. Why do we strive for simplicity? What is the value of trying to go for the simplest possible model that explains the most variance? But it is a principle to aim for when doing data investigations. Finally, and perhaps the most overlooked part of data science, communication. You need to be able to effectively communicate your story. You could have performed the most effective data analysis on the most complex data that anyone has ever seen. But if you can't tell people effectively what story is in that data, there's really no use to the analysis. The purpose of doing data science is to understand a set of relations and convey that to others and in a simple and principled way. So communication is a critical part of data science. And at the end of this course, we'll learn how to effectively communicate what your results are, what your data is telling you, and communicate uncertainty in the process. Admit what you know for certain and what you are uncertain about. Now, all 8 of these principles of data investigation all work collectively together in the general inference of the scientific method. And often we talk about the logic of the scientific method by going over Walter Wallace's logic wheel. And this is a schema of processes that describe how the scientific approach should work in theory. And on one side, you have deductive methods, shown here on the right. So these are methods by which you remove sources of information in order to get down to some hypothetical truth. On the other side, you have inductive methods, where you try to put things together in order to understand relations. And induction and deduction work together in science. So you start with some theory. In this case, a high level theory that has some broad understanding of the mechanisms of the world. And in this theory space, you don't have to be constrained necessarily by ability to collect data or by realistic assumptions of what your data will look like. It's just your thoughts on the real world. But then what you do is you take that theory and you operationalize your definitions, you constrain it in such a way that you can deduce the consequences of relations in your data and make predictions. Those predictions and that set of relations is your hypothesis. This is the critical step in science, is the formation of a hypothesis. Once you have a hypothesis, then what you have to do is you design tests for specific observations. You've gone from some high-level theory about the way the world works to a very specific testable hypothesis of a set of relations between some variables x and some variables y. And then you go and collect those x's and those y's that are very specific. And you look at those observations. From those observations, you determine the outcome of those tests. And more importantly, you try to generalize those outcomes to new things, either unseen data in new situations or completely novel situations that require collecting new data. But in that generalizability, this ability to say, my hypothesis can explain not only these observations, but makes these future predictions, you reframe and refine and redevelop propositions that change your theory. And then you start the whole cycle over again. The process of science, as described by Wallace's logic wheel, is the same process of data science. You have some theory about the way the world works. You form a hypothesis, in this case, the form of a model with which you're going to analyze your data. You take a set of observations and test your model against it. You evaluate the generalizability of that relationship. And then you use those observations to refine your high-level theory. Data science is a science, and so it follows those exact same logical processes. Now, sometimes, well, maybe not even sometimes, a lot of times, you need to be able to see past the data as well. And this is where data science goes from a science to an art. And let's think about this from a classic example. Abraham Wald was a statistician in World War II. He was instrumental in developing a lot of early theory in statistics and probability theory. Wald was faced with a dilemma. The generals wanted to know, where do they need to reinforce planes going into combat in order to reduce the number of downed aircraft during battle? Essentially, where do you put more armor on planes? So the data that Wald was given was a map that you see here on the left, showing points on a particular plane model where bullet holes were observed on planes that came back from battle. So this is the set of data that Wald was tasked with analyzing in order to know where to put more armor on planes. Now, if you don't have a deeper intuition of the data, your principal, or at least first pass assumption, is to put more armor where there are more bullet holes. Seems logically sound, right? But Wald knew that he was only looking at planes that had come back from battle. There was a survivor bias. So he wanted to know, why don't we see bullet holes here? It's because the planes that get hit in those areas don't tend to return back to base. So Wald had the appropriate intuition that it is these areas with the least dense bullet holes when planes return that need to be up-armored the most. And this example shows why you need to have a deep understanding of the nature of your data before you can really infer anything from it. A lot of statistics done early on by students in data science is very plug and play. I have a model, a linear discriminant analysis. I have a set of X, and I have a set of categories. What are my patterns? Can I classify these groups? That's not the question you should start with. You should start with, what is my data? Where does it come from? How is it distributed? What is my thought about the nature of the relationships in these data? What would be the appropriate way of looking at those relationships? What are the alternative methods by which this data could have arisen? What are the alternative hypotheses that this data could reinforce? All of these more nuanced questions about your data and the relations they're supposed to reveal are critical. And I want you throughout this course to be thinking carefully about this underlying nature of the data set that you'll be working with. Okay, so spent some time going over the theory of the field of data science, where it is, where it comes from, what you do with it. Now let's focus on more minutiae details on this class itself. Now, the principal goal of this class is to make you all more effective data detectives by showing you how to extract intuition and knowledge from your data. Not just information, but true knowledge and understanding. Hopefully, after completing this course, you will be able to understand basic principles of statistical theory, measurement, and experimental design. You should be able to clean and organize data effectively. You should be well versed in the execution and interpretation of data analysis. You should be able to use information resources to find appropriate data science tools. You should be able to communicate statistical results effectively in multiple modalities. And you should be a critical consumer of data science techniques and their application in empirical research. And this last objective is the one I want to focus on the most. Even if you don't work with data science ever again after this class, hopefully you'll have the content knowledge necessary to be a critical consumer of research and data science results in the future. So when you read a news story that shows a graph proposing a hypothetical relationship between variables, you can look at it carefully and deeper than a naive reader and understand the nuance behind the data, the complexity of the relationships beyond what the reporter or news summarizer wants you to know. So these goals are big. I'm going to assume some prior knowledge here. For this class, I'm going to assume an introductory level understanding of probability theory and statistics. Do you know what a normal distribution is? Do you know what a mean is? Do you know what a standard deviation is? Do you know what a t-test is? How about a correlation? How about an ANOVA? If you know all of these items that I just listed, you'll be able to do just fine in this class. At Carnegie Mellon University, this is covered in classes like 36309, 86309, or equivalent. If you don't have this background knowledge, I recommend pausing and going to one of the many open access education sources online to go over this basic background knowledge. I'm also going to assume a basic familiarity with R or similar functional data analysis languages, Stata, if you've worked with macros in SPSS, if you have to, Julia, MATLAB, but anything where you kind of have functional-oriented programming. You don't have to be an expert in it. I'm just going to assume that you're comfortable with it. We'll try to get you up to speed in the tutorials of this class, but having a basic familiarity with R or a similar language will be helpful. Now, this is a flipped class. So there's actually two portions to the learning structure of the class. There's an asynchronous offline portion and a synchronous online portion. Prior to every in-person or online synchronous portion of the class, you're expected to do the required reading, watch a short video lecture like the one you're watching now. They're about 30 to 40 minutes long. And go through the tutorial on the Jupyter book for this class. The Jupyter book is called Data Explorations. So when we come into the live synchronous class time, which can either happen in person or over Zoom. There will be a short question and answer period at the beginning of each class period where I will answer questions regarding the reading and the content knowledge that happened before class. We will then do breakout discussions where we'll break into small groups of anywhere between 3 and 6 people and answer a very specific discussion question selected on each class. And these questions are designed to dig deeper into the content knowledge that you learned before class. And then at the end of class, we'll all come back together and have an open discussion, really summarizing the talking points that happen or the discussions that happen during the breakout sessions. Now, the overall goal here is to learn all the content knowledge up front, get that crystallized knowledge prior to class, and then engage in a dynamic discussion, this more fluid intelligence, fluid understanding during the class itself. From here, in this kind of a method, you can learn the content knowledge at your own pace. If you need to rewatch a lecture, if you need to spend more time reading, you have that. You're not expected to consolidate all the information possible in a 60-minute or 80-minute class. That way, the class time itself is really reserved for kind of pushing through this fluid understanding, this fluid intelligence of the concepts we're trying to learn and how they relate to other topics that we've discussed throughout the semester. Okay, the resources for this class are pretty straightforward. There's a Jupyter book, which has been written over the past few years by myself and previous teaching assistants in the class. It's called Data Explorations. You can see the URL up there. We also have a link to this in the syllabus. The only required textbook right now is James et al., An Introduction to Statistical Learning with Applications in R. I'm going off the 6th volume, but they're all pretty similar. One thing to note, there is another book by, I think, most of the same authors called An Introduction to Statistical Learning, and it doesn't say the colon phrase with applications in R. Don't take that book. Look for the one that says with applications in R. The one that just says An Introduction to Statistical Learning is a more advanced machine learning book that's meant for graduate level machine learning students. There's also a supplemental book which I recommend highly and will base some of our early work off of, but it's just a good book to have around, which is the Wickham's book R for Data Science. So you're not required to get it, but it would be immensely helpful for completing the class. There's also auxiliary readings that are posted on Canvas and the GitHub sections of the class. These are individual papers. Sometimes they're reviews, sometimes they're analytic papers. And actually a bulk of the reading for the first half of the class will be through these auxiliary readings. There's also a GitHub repository for this class. The URL is right there. And most of the major content will sit on GitHub as well as the closed Canvas site for the class. So if you're taking this class publicly and you're just watching the videos and you want to learn the content on your own, all the information that you're going to need, all the content you're going to need will also be on the public GitHub repo. I just want to point out one thing from that repo. If you go to the wiki page on the repository, we have a lot of very helpful links to resources, the required tools like R and Jupyter Notebooks, GitHub, etc., RStudio, GitKraken, Jupyter Themes, useful links for catching up on prior material, etc. So keep checking that wiki. We keep updating it throughout the semester, and hopefully it has some useful information for you. Okay, that's it. We have officially given an introduction to this course, and look in the syllabus and follow up on the next sets of lectures and the Jupyter book to start digging into applied data science for psychology and neuroscience.